Hello, everybody, and welcome back to another video in Geography 340 Climatology. I am Dr. Zach Hilgendorf, and in this video, we're going to be focusing on precipitation. We talked about clouds, we talked about how air parcels move. Now let's focus on what happens when they do move. We typically see this expressed as precipitation on the surface of our planet, whether that's snow or ice or hail or virga or some of the more exotic versions like occult. So let's go ahead and start talking about that. So first off, let's just look at our global patterns of precipitation. You see them here. The majority of the rainfall occurs in the northern portions of South America, Central Africa, and kind of the Pacific Islands, so Indonesia, Papua New Guinea, all these different islands through north of Australia, so Oceania region. So we're going to focus on first precipitation processes. So we have cloud formation, right? These cumulus clouds or cumulonimbus clouds forming cumulonimbus clouds, and cumulonimbus clouds leading to, broad rainfall, or nimbostratus clouds leading to long all-day drizzles, right? These different types of cloud formations occur, but what type of precipitation do they produce? Well, in the last video, we talked about what clouds are, these atmospheric particulates of water that form. So that particulate part is the most important part, because what we have, and as clouds form, we've learned how they form, but what are they? Well, they're liquid droplets and solid particles suspended in air. That's really all they are. They have a low terminal velocity, which means they're not hurtling down towards the surface of our planet quickly. They're able to be maintained in a buoyant state within our atmosphere. Particles, or these particulates, typically have a diameter of about 10 to 20 micrometers. Next question is, what is precipitation? Well, water, like liquid or solid, that falls from clouds to the surface. What do you need for precipitation to happen? Well, you need large cloud particles, whether that's liquid or solid, with a high terminal velocity. They need to move towards the surface. They can fall to Earth before evaporating or sublimating. And there are effective mechanisms for cloud particle growth. So here, we look at our parcel of air again, 25 degrees Celsius, our dew point's 21 degrees Celsius. We rise 500 meters, so they both are 20 degrees Celsius. That's our lifting condensation level. And we have the development of clouds at this lifting condensation level. Well, at that lifting condensation level, you can see it here, that dashed blue line. Here's our condensation nuclei. Diameters of about 1 micrometer or so. And as you condense, once we hit that lifting condensation level, water is condensing to this particulate matter. And if it has enough time to develop, it starts to develop these clouds, and we see more and more condensation on these nuclei. By about 50 meters above the lifting condensation level, the number of droplets per cubic meter equal billions, which is pretty astonishing, right? Here we see 10 micrometer droplets have a volume of about 524 cubic micrometers. 1 micrometer droplets have a volume of about half a cubic micrometer. Our 20 micrometer droplets have a volume of about 4,200 cubic micrometers. And our 500 micrometer droplets actually have a volume of about 65 million cubic micrometers. So the bigger droplets have obviously much mass. There is more of them. It's easier to have much more mass in general. So how do cloud droplets grow into raindrops? Primarily through these collision and coalescence processes. So what you have is a collector drop colliding with smaller drops. Due to compressed air beneath the falling drop, there's an inverse relationship between the collector drop size, and the collision efficiency. Collision typically occurs between a collector drop and a fairly large cloud drop. Smaller drops are pushed aside. Collision is more effective for the droplets that are not very much smaller than the collector drop. When collision occurs, drops either bounce apart or coalesce into one larger drop. Coalescence efficiency is very high, indicating that most of these collisions are going to result in a coalescence, so the drop is going to expand in size. Collision and coalescence together form the primary mechanisms for precipitation, especially in the tropics where warm clouds dominate. Here's what we see when we see a warm cloud. So the physical processes involved in transforming a cloud of very tiny droplets to much larger precipitation-sized particles that fall on the ground is incredibly complex and not really that well understood, if we're being honest. In warm clouds, those that contain only liquid water, droplets grow by this process of collision and coalescence, in which colliding droplets grow by merging together and coalescing. Larger droplets fall faster than smaller droplets, and thus continue to grow as they fall through the smaller droplets. Just as with hail, strong updrafts or rising air currents can form large raindrops because they allow heavier drops to remain suspended in the cloud for longer. In cold clouds, precipitation-sized particles form by what we call the Bergeron process. When the temperature in a cloud is between 0 and negative 40 degrees Celsius, there exists a mixture of ice crystals and supercooled water droplets. Supercooled water is just water that remains liquid even though the temperature is below the normal freezing point of 0 degrees Celsius. The reason for this is that the tiny water droplets generally don't freeze until the temperature drops below negative 40 degrees Celsius unless they contain a special type of cloud condensation nucleus called an ice condensation nucleus. Often there's a scarcity of ice condensation nuclei in the atmosphere. Therefore, when the in-cloud temperature is between 0 and negative 40 degrees Celsius, there are usually many more supercooled liquid droplets than ice crystals. This observation is also important in the formation of lightning and hail. So in the Bergeron process, ice crystals grow as water vapor deposits onto crystals, while the supercooled liquid water droplets evaporate. This occurs because the saturation vapor pressure for water is higher than that of the saturation vapor pressure for ice. The result is that ice crystals grow large enough to begin falling from the cloud. On the way down, the crystals may grow even larger as they contact supercooled droplets of other ice crystals. Aggregation is the joining of multiple ice crystals through surface water bonding, building ice crystals to a point of overcoming updrafts. We can see that here. Notice how they are fused together in this example. It's our aggregation example. Compared to riming, which is the process by which liquid water freezes onto ice crystals, producing rapid growth. We see that here and here. That's kind of how chunky these look. That's riming occurring. So we have our cool clouds like those here, driven by that cold front pushing through that rapid rise of air on the leading edge of the cold front. So here, say if we're looking vertically, our temperature might be 0 degrees Celsius at this point in the atmosphere. Negative 40 up here. You can see examples of what happens once you get this cloud development here. So now let's move into types of precipitation development, types of precipitation, pardon me. So we're going to start off with the really easy one, rain and snow. But let's go ahead and first focus on rain. You can see it here, it's all around us. It prevails during our summer months, right? So rain is obviously liquid water that drops and hits the ground. Because the temperature in clouds is often well above freezing, it is very common that rain on the surface left the cloud as snow, especially in the winter before melting on the way down. Evidence for this can be observed in mountainous areas when the same storm produces snow on the mountains and rain in the valleys. Depending on the complex combination of microphysical processes and larger scale atmospheric conditions such as relative humidity and updraft speeds, raindrop sizes range from small drops of drizzle or mist less than 1 millimeter in diameter to large drops over 5 millimeters in diameter. So in this example here, this rain has been rain the whole time, right? We're above 0 degrees Celsius from the temperature profile. So the base of the cloud is where that line starts, the lifting condensation level there. And as the rain falls, it warms in temperature towards the surface. So here we can see that it has been rain the whole time, but that's not always the case. As we said, sometimes it can start as snow, and as it drops in the atmosphere and crosses over that line of 0 degrees Celsius or 32 degrees Fahrenheit, it can start to warm and it will melt and will become rain. See here. So everyone thinks of rain as these beautiful drops, right? Because that's what rain looks like. Not quite. Usually starts off as these droplets, these spherical droplets of water, around 2 millimeters or so. As the frictional drag increases, these raindrops change to almost more of a mushroom shape as you go along. You can kind of see in that image there, those are circular drops, and that's what you expect, or spherical drops, pardon me, and that's what you expect. So you can see those forces acting as that raindrop grows in size. The collector drop as it's collecting more. Here you can see frictional forces continuing to act. You kind of see that dominant mushroom shape occurring now. Drops split when the frictional drag force overcomes the surface tension of the water. Splitting ensures that a maximum drop size of about 5 millimeters is consistent, and the continuation of the collision and coalescence processes continue. Go to this site here if you want to see kind of a better example of the anatomy of a raindrop. Next, we're going to move on to snow. Snowflakes are simply aggregates of ice crystals that collect to each other as they fall towards the surface. The size and shape of snowflakes are quite varied depending on the atmospheric conditions under which they formed. Snowfall distribution in North America is related to the north-south alignment of mountain ranges and the presence of the Great Lakes typically. So here in this example, we see our temperature profile. Here again, it is snow the whole way down because it has never gotten warmer than that 0 degrees Celsius after the precipitation in the form of snow fell from the cloud. Beautiful, right? I love it. I'm a big fan of snow. Currently, there is snow cover leading into the week of Thanksgiving when I was recording this. So that was exciting. My first winter back in the Midwest after living in Arizona for a number of years. So I'm very, very pleased and happy to have snow again. You can see these beautiful examples of these kind of the crystalline lattice work here that snow flakes often form. Next, we're going to move on to graupel. Graupel is a type of snow pellet, which is often mistakenly referred to as hail. It is white, opaque, approximately round precipitation particles, typically between 1 and 2 inches in diameter. Sorry, 0.1 and 0.2 inches in diameter. They are crisp and easily crushed. They bounce when they hit the surface. Squalls of graupel occur primarily during the fall and spring months as a result of extreme instability in the Great Lakes region. So you can see it lining the road here and here as well, like kind of those smaller pellety precipitation that you might have seen previously. They also can grow through the process of riming. You see here that snowflake, the riming occurring, and kind of this pellet form kind of prevailing. You can see it here as well. Sleet is the next one we'll talk about. Sleet begins as ice crystals which melt into rain through a mid-level temperature inversion before solidifying in colder, near-surface air. Sleet is less prevalent than freezing rain and is defined as frozen raindrops that bounce on impact with the ground or other objects. Sleet is more difficult to forecast than freezing rain because it develops under more specialized atmospheric conditions. It's much less troubling than freezing rain because it is easy to see and is already frozen before it hits the ground. So here you can see in this little diagram from the National Weather Service, Missoula, sleet on the left, liquid precipitation that freezes before reaching the ground, versus graupel, snowflake that collects supercooled water droplets onto its surface, forming these pellets. And kind of forms through this process here. So you have maybe snow in the upper portions of the atmosphere where the clouds are, melting into rain and then freezing again. So we have this almost thermal inversion midway into the atmosphere. And as it cools down again, it forms that sleet. A lot of times you can see this when you have this wedge of warm air, kind of a warm front moving through. So you have cold environmental air falling into this warm front, this wedge of warm air pushing over the cold air, and then refreezing again as sleet once it falls through that warm front layer back into the colder air. We've got freezing rain next. When you hear news of an ice storm, it's freezing rain. Ice storms can be the most devastating thing that we have, winter weather phenomena, and are often the causes of automobile accidents, power outages, and severe personal injury. Ice storms result from the accumulation of freezing rain, which is rain that becomes supercooled and freezes upon impact with cold surfaces. You can see here, looks pretty, very deadly. You kind of see a similar example to sleet, but kind of have this appendage here where stays warmer until it kind of hits right at the surface there. And once it hits that colder surface, like frozen surface or sub-zero surface, it will freeze again. So freezing rain develops as falling snow encounters a layer of warm air deep enough for the snow to completely melt and become rain. As the rain continues to fall, it passes through a thin layer of cold air just above the surface and cools to a temperature below freezing. However, the drops themselves do not freeze. When the supercooled drops strike the frozen ground, or power lines, trees, branches, etc., they instantly freeze, forming a thin film of ice, hence freezing rain. A prolonged period of freezing rain results in a thick layer of ice covering everything. An intense ice storm can paralyze a region in a matter of hours, greatly affecting the people who live there. Freezing rain is dangerous because it is almost invisible on smooth surfaces and, consequently, dangerous to people trying to walk over it. We can see that similar formation here. It can be pretty drastic when it does happen. Next, hail. You can see examples of hail here and here and here, quarter sized in this example. This fine gentleman wearing a Dakota Land hat, nice hat, holding quite a large piece of hail. Here, these are from South Dakota in 2010, weighed nearly 2 pounds and 8 inches in diameter. So hail forms as concentric layers of ice build around graupel. It's formed as graupel is carried aloft in these drastic updrafts here. At high altitudes, water accreting to graupel freezes, forming a layer. Hail then plummets, but if it's caught by another updraft, the process of adding layers will repeat. The ultimate size of the hailstone is determined by the intensity of those updrafts. Most hail events in North America occur over the Great Plains. You can see here, this is kind of how you describe the size of hail. from BB sized to softball sized. This is from weather.gov. The most hail in, in the United States occurs, as I said, over that Great Plains region. We can kind of see it here, kind of right along the front range of the Colorado Rockies and kind of extending into Nebraska, Kansas, Oklahoma, Texas, and South Dakota. Here you can see an example, a perfect one of that, of golf ball sized hail. Notice those concentric rings that you're seeing there as it's lifting through the atmosphere and more water is accreting to that surface, freezing, adding a layer. You can see it here as well. Quite beautiful if it wasn't a hurtling ball of pain. Occult, this is a weird one, horizontal movement here. On Inselbergs and mountain masses within the tropics, the summits are frequently covered in clouds in locations where the orographic uplift of the moist air is sufficient to cause condensation. If the upper slopes are covered in forests, the surfaces of the branches of trees act as collectors for condensed water vapor. This phenomena is referred to as occult precipitation because it does not relate to any rainmaking process in the clouds itself, and rain gauges placed outside the forest area will not record any rain at all. Kind of weird or eerie, occult in nature, if you will. See that here and here. And here. You see those water droplets forming on the plants in these rainforest regions. And finally, the process Virga, also called Fallstreifen, fall streaks, precipitation trails. These are wisps or streaks of water or ice particles falling out of a cloud, but vaporizing before reaching the Earth's surface as precipitation. Virga is frequently seen trailing from altocumulus and altostratus clouds, but also is discernible below the base of high-level cumuliform clouds from which precipitation is falling onto a dry subcloud layer. So I'd like a dry air mass, think of it that way. It typically exhibits a hooked form in which the streaks descend nearly vertically just under the precipitation source, but appear to be almost horizontal at their lower extremities. Such curvature of virga can be produced simply by the effects of strong vertical wind shear, but ordinarily it results from the fact that droplets or crystal vaporization decreases the particle's terminal fall velocity near the ends of the streaks. Virga is associated with dry microbursts, which are formed as a product of the vaporization process. So, as a quick recap, in this video we talked about global precipitation distribution, the requirements for precipitation, how precipitation forms, and the different types of precipitation. I hope you enjoyed this video. We're going to be talking about mid-latitude cyclones and hurricanes in the next videos, and I will see you there. Thanks.